Stars illuminate the vast darkness of space. They are the beacons of the night, guiding us through the cosmos with their radiant light. Each star, a distant sun, holds secrets of the universe within its fiery core. From the moment they ignite, stars begin a journey that spans millions, sometimes billions of years. They are born from clouds of gas and dust, collapsing under their own gravity, igniting nuclear fusion in their cores. This process releases an immense amount of energy, causing the star to shine brightly in the night sky. They twinkle like celestial diamonds, their light traveling across the vast expanse of space to reach our eyes. This twinkling is caused by the Earth's atmosphere, which bends the starlight as it passes through. Each twinkle is a reminder of the star's distant presence, a tiny flicker of light in the immense darkness. Stars come in various sizes and colors, from small red dwarfs to massive blue giants. Their color indicates their temperature, with blue stars being the hottest and red stars the coolest, but their lives, like ours, are finite. Stars go through a life cycle from birth to death, and their fate depends on their mass. Smaller stars, like our sun, will eventually swell into red giants before shedding their outer layers and leaving behind a dense core called a white dwarf. Larger stars, however, have a more explosive end. Some stars end their journey with a whimper, fading into obscurity. These stars quietly exhaust their nuclear fuel, gradually dimming until they no longer shine. They become white dwarfs, slowly cooling and fading over billions of years. These remnants are like cosmic embers, the last vestiges of a once brilliant star. Others, however, choose a more dramatic exit. These massive stars, many times the size of our sun, end their lives in spectacular fashion. When they exhaust their nuclear fuel, their cores collapse under the force of gravity, leading to a cataclysmic explosion. They explode with the energy of a billion suns. This explosion, known as a supernova, is one of the most powerful events in the universe. It can outshine an entire galaxy for a brief period, releasing more energy in a few seconds than our sun will in its entire lifetime. This is a supernova, the awe-inspiring death throes of a star. The explosion sends shockwaves through space, creating new elements and scattering them across the cosmos. These elements are the building blocks of everything we see around us. Supernovae are not merely destructive events, they play a crucial role in the evolution of the universe. The remnants of these explosions, known as supernova remnants, are rich in heavy elements like carbon, oxygen, and iron. They are crucial for the evolution of the universe. These cosmic explosions scatter elements heavier than hydrogen and helium across the cosmos. These elements are essential for the formation of new stars, planets, and even life itself. These cosmic explosions scatter elements heavier than hydrogen and helium across the cosmos. The debris from a supernova can trigger the formation of new stars, continuing the cycle of stellar evolution. The elements created in these explosions are also found in planets, moons, and even in our own bodies. These elements are the building blocks of planets, of life itself. Without supernovae, the universe would be a much simpler place, lacking the diversity of elements needed for complex structures. In a way, we are all made of star stuff, forged in the fiery deaths of ancient stars. A supernova is a powerful and luminous stellar explosion. These cosmic events are not just ordinary occurrences, they are the dramatic deaths of massive stars. When a star reaches the end of its life cycle, it undergoes a cataclysmic transformation that results in a supernova. This process is one of the most fascinating phenomena in the universe, captivating astronomers and stargazers alike. It occurs when a star has exhausted its nuclear fuel and can no longer support itself against its own gravity. The star's core, which was once a bustling hub of nuclear reactions, becomes a dense and inert mass. Without the outward pressure from nuclear fusion to counteract gravity, the core succumbs to its own weight. The star's core collapses, releasing an immense amount of energy. This collapse happens in a matter of seconds, but the energy released is so vast that it can outshine entire galaxies. The core collapse triggers a shockwave that travels outward, causing the outer layers of the star to explode violently. This energy blasts the star's outer layers into space. The material ejected from the star travels at incredible speeds, spreading out into the surrounding space. This ejected material can form new stars and planets, seeding the cosmos with the building blocks of life. Supernovae are among the most energetic events in the universe. They release more energy in a few seconds than our sun will emit in its entire 10 billion year lifetime. These explosions are so powerful that they can trigger the formation of new stars by compressing nearby gas clouds. They can briefly outshine entire galaxies. For a short period, a single supernova can be more luminous than all the stars in its host galaxy combined. This incredible brightness makes supernovae visible across vast distances, allowing astronomers to study them even in distant galaxies. The light from a single supernova can be visible across billions of light years. This means that we can observe supernovae that occurred billions of years ago, providing a glimpse into the distant past of the universe. These observations help scientists understand the life cycles of stars and the evolution of galaxies. These events leave behind beautiful and expanding clouds of gas and dust called supernova remnants. These remnants are not just visually stunning, they are also scientifically significant. They contain heavy elements that were forged in the heart of the star, enriching the interstellar medium and contributing to the chemical diversity of the universe. The study of supernova remnants provides valuable insights into the processes that shape our cosmos. There are two main types of supernovae, Type 2 and Type Ia. Type 2 supernovae occur when a massive star, at least 8 times the mass of our Sun, runs out of fuel and collapses under its own gravity. This collapse triggers a shock wave that rips the star apart. Type Ia supernovae, on the other hand, involve a white dwarf star in a binary system. The white dwarf steals material from its companion star. When the white dwarf accumulates enough mass, it reaches a critical point and explodes. Stars are giant nuclear reactors. They spend most of their lives fusing hydrogen into helium in their cores. This process releases the energy that makes stars shine. However, when a star runs out of hydrogen, it begins to fuse heavier elements. During a supernova, the intense heat and pressure create even heavier elements such as gold, silver, and uranium. These elements are scattered into space by the explosion. They enrich the interstellar medium, the space between the stars. Section 5. Scattering stellar ashes. Seeds of new beginnings. Supernova remnants are not just beautiful objects, they are the spectacular end stages of massive stars, which have exhausted their nuclear fuel and exploded in a brilliant display of light and energy. These remnants, often seen as colorful nebulae, are the ashes of stars that once shone brightly in the cosmos. They play a vital role in the cycle of star birth and death. The universe is a vast, dynamic place where stars are born, live out their lives, and eventually die, only to give rise to new stars. This cycle is essential for the evolution of galaxies and the creation of complex elements. The expanding shock waves from supernovae can compress nearby clouds of gas and dust. These shock waves travel through space, colliding with interstellar material and causing it to clump together. This process, known as shock-induced star formation, is a critical mechanism in the birth of new stars. This compression can trigger the formation of new stars. When the gas and dust are compressed enough, they can collapse under their own gravity, leading to the formation of a protostar. Over time, this protostar will gather more material, heat up, and eventually ignite nuclear fusion, becoming a new star. The elements forged in supernovae become part of these new stars and their planets. Supernovae are responsible for creating many of the heavy elements in the universe, such as gold, silver, and uranium. These elements are scattered into space by the explosion and can be incorporated into new star systems. Our own solar system formed from a cloud of gas and dust that was enriched by the remnants of previous supernovae. This protoplanetary disk contained all the elements necessary to form the sun, planets, moons, and other bodies in our solar system. The heavy elements from supernovae played a crucial role in the formation of rocky planets like Earth. This is why Earth contains elements heavier than iron. These elements, which are essential for life and technology, were created in the hearts of dying stars and spread throughout the galaxy by supernova explosions. Without these cosmic events, our planet would not have the rich diversity of elements that make life possible. Section 6. Supernovae and the seeds of life beyond Earth. The elements dispersed by supernovae are essential for life as we know it. Carbon, oxygen, nitrogen, and other elements found in our bodies were all created in the cores of stars and during supernova explosions. Some scientists believe that supernovae may have played a role in the origin of life on Earth. The shock waves from nearby supernovae could have delivered organic molecules to the early Earth. These molecules could have then become the building blocks of life. Section 7. Supernovae in History Celestial Fireworks. Throughout history, humans have witnessed the spectacular light shows of supernovae. In 1054 AD, Chinese astronomers recorded a guest star in the constellation Taurus. This supernova was so bright that it was visible during the daytime for 23 days. The remnant of this supernova, now known as the Crab Nebula, is still visible today. It provides valuable insights into the dynamics of supernova explosions. Other historical supernovae have left behind equally fascinating remnants. Section 8. Our Galactic Future, a tapestry woven by supernovae. Our galaxy, the Milky Way, experiences an estimated 1 to 2 supernovae per century. Each explosion sends ripples through the interstellar medium, shaping the galaxy's structure and evolution. The ongoing cycle of starbirth, death, and rebirth ensures that our galaxy will continue to evolve. Supernovae, while marking the end of a star's life, play a vital role in this ongoing cosmic dance. They are the ultimate cosmic recyclers, scattering the seeds of new stars and planets throughout the universe.